the blue man here is going around the equatorial linear speed of about 1,000 miles an hour. But the question is, can he feel it? And again, we do not feel speed, we feel acceleration. So we need to talk about the acceleration of our blue man. So again, he's right here, and he's spinning around. Okay? Centripetal force is the force needed to keep things in circular motion. Because if there's nothing keeping them in circular motion, they will just fly off. You can't spin something without the string connected. String breaks, it no longer stays in its circular motion. So F is equal to mass times acceleration. And in this case, I'm going to say F sub c for centripetal is equal to the mass of the centripetal acceleration. And centripetal acceleration is v squared over r. So in this case, mass stays the same. V is velocity. This is our velocity. Velocity squared divided by the radius. And here we have the radius. Now, sometimes it is important to talk about force. Other times, all we really want to talk and think about is the acceleration. So centripetal acceleration is v squared over r. This is what we use to figure out the acceleration on an object, or whether we would feel it. In this case, 1,041 miles per hour squared divided by the radius, which is 4,000 miles, (1041) squared divided by 4,000 is equal to 271 miles squared, hours squared, miles per hour squared. The units of acceleration are distance over time over time. 270 miles per hour squared, which means there's an additional 271 miles added every hour. We usually don't have these units for acceleration. Acceleration is usually given in meters per second or feet per second. So again, the most common problem in physics is mistake of units. So we'll take this 271 miles over hours squared, and we want to turn it into feet per second. So we need to multiply it by a conversion factor that will turn our miles into feet. So if I have a mile upstairs, I'm going to want a mile downstairs so that they will eventually cancel out. So 1 mile is equal to 5,280 feet. And in this case, the mile downstairs cancels the mile upstairs. We're left with feet upstairs. We also want to convert hours squared into seconds squared. Now this gets a little bit more complicated. Hours on the bottom, so we're going to want an hour on the top. 1 hour. In 1 hour, there are how many seconds? There's 60 minutes, and then there's 60 seconds in each of those. So it's 60 times 60, 3,600 seconds. Now if we use this as our conversion factor, our hour will only cancel one of these hours, and we'll be left with another hour in the denominator. So we actually need to square this conversion factor, conversion unit. Again, unit means 1. 1 hour over 360 seconds is 1. So you can multiply it by 1 all day long without changing the value. And 5,280 feet is the same as 1 mile. So again, that is a unit, conversion unit. So these hours squared will cancel these hours squared. We'll be left with a second squared in the denominator. So we're going to have 271 times 5,280. Unit will be feet, divided by 3,600 squared, seconds squared. All right, I will 271 times 5280. I'm going to divide that by 3600. Then I'm going to divide it by 3600 again. We get 0.11 feet per second squared. So this is the equatorial acceleration, the equatorial centripetal acceleration, 0.11 feet per second squared. The question we keep coming back to is, can you feel it? So back up here. The acceleration on this fellow toward the center, the centripetal acceleration is 0.11 feet per second squared. So if it is spinning, there is this much acceleration required to keep him in the circular motion. The centripetal acceleration is always toward the center or axis of rotation. So if he is being pulled this way, again, when the car turns left, the force is to the left, but it feels like we're being pulled to the right. So again, I am using the red vector to show the centrifugal effect. It feels like he's going to fly off. It feels like he's being pulled off. How much? 0.11 feet per second squared. Is that enough to feel? Well, the acceleration due to gravity, or the acceleration that we can empirically find here on Earth, is 32 feet per second. The acceleration due to gravity, or the gravitational effect, is 32 about feet per second squared. So, free body diagram says we can draw our little guy, and we can draw the forces or the acceleration acting on him. So toward the center of the Earth is the acceleration due to gravity, and the centrifugal effect seems to be pulling him off the planet. It has been said that the Earth is spinning 1,000 miles an hour and we would fly off at the equator. The acceleration due to gravity is toward the center. The centrifugal effect is in the opposite direction. So this is the acceleration. The centripetal acceleration is equal in magnitude and opposite in direction to the centrifugal effect. It is a fictitious force. However, they do act equal and opposite. So in this case, the acceleration due to gravity is 32. The acceleration due to the rotation is 0.11. They're in opposite directions, so we can simply subtract them. 32 minus 0.11. What do you guess? 31.89 feet per second squared. 31.89. When you're standing at the equator, you're being forced down at an acceleration of 32 feet per second squared. As it's spinning, the centrifugal effect is 0.11 feet per second squared. So if at the equator, the force pulling me down is smaller than at the pole. As we saw, the person at the pole is dealing with no centripetal motion. He's just turning around in circles very slowly. So if this fellow up here weighs, now weight is actually a force, not a mass, but we'll use it for here. If this guy weighs 200 pounds, how much does this guy weigh? He's going to weigh less because there is an effect of him seeming to fly off, but it's very small. So his weight at the pole divided by his weight at the equator is equal to the acceleration at the pole divided by the acceleration at the equator. The acceleration at the pole is just acceleration of gravity because there is no canceling out piece. And the acceleration at the equator is equal to this reduced figure, 31.89. 32. 200 at the pole, question mark at the equator. So we're going to cross multiply to solve this. Multiply the 31.89 times the 200, then divide it by 32, whereas we're multiplying the question mark over to the other side. So we have 200 divided by 32 times 31.89. Question mark, or your weight at the equator, 199.3 pounds. So the question is, can you feel the acceleration due to the spinning of the Earth? Can you feel it at the equator? If I weigh 200 pounds at the pole and 199.3 at the equator, that's a difference of 0.7 pounds. It's like 2/3 of a pound. A pint of water weighs 1 pound. So that's like 12 ounces of water. If you drink 12 ounces of water, you will be back up to your 200. So my question is, can you tell how much you weigh before and after 12 ounces of water? I can't. My weight fluctuates 6 or 7 pounds throughout the day, depending on hydration, exercise, and other factors. The acceleration that we feel that we would be subject to at the equator on a spinning globe, turning once every 24 hours with a linear speed of over 1,000 miles an hour, the actual effect on us is 2/3 of a pound out of 200. That's 1/3 of a pound out of 100. So, again, I don't think if you stand at the North Pole you can feel yourself turning. And I don't think if you stand at the equator you can feel the difference in your weight due to the centrifugal effect. We'll pick this up next time with G-forces. Thanks for watching.